Let's dive right into today's explainer, where we are going to figure out exactly how to keep your food ice cold with solar energy when the grid goes completely dark. If you've ever, stared at a solar panel and then looked at your refrigerator and wondered how on earth to connect the two without totally ruining your groceries, or worse, frying your equipment, well, you're in exactly the right place. Because whether you're an off-grid camper deep in the woods or just prepping for those super unpredictable summer power outages, trying to nail down the electrical math to run a fridge on solar can feel, well, incredibly intimidating. I mean, we're essentially talking about converting sunlight into ice. And if you get the math wrong here, you aren't just out of power, you're literally throwing away hundreds of dollars in spoiled food. But hey, don't worry, we're going to break this whole thing down so it makes complete practical sense. So here is our roadmap for today. We'll be covering continuous and surge power, daily energy consumption, inverter losses, battery autonomy, solar panel calculation, and finally, practical application. By sticking to these 5 distinct steps, we can take what looks like this huge, complex engineering puzzle and turn it into a completely manageable, actionable plan. Seriously, you absolutely do not need an electrical engineering degree for this. You just need to follow the logic. All right, let's jump into step 1, continuous and surge power. So the very first thing we need to do is find out exactly how much power your fridge needs just to turn on and, stay on. This is the bedrock of our entire solar sizing project. To make this super clear, throughout this explainer, we're going to compare 2 setups side by side. For our small setup, we've got a chest freezer pulling 196 continuous watts. And for our large setup, a full-size home fridge drawing 495 watts. Wondering where to find these numbers for your own gear? Just open the door or peek at the back panel. You'll usually find a manufacturer's spec plate with the voltage and amperage. Just multiply those 2 together and boom, you've got your continuous wattage. But okay, here is the hidden gotcha that trips up almost every novice: surge power. Surge power is this really brief but massive peak in energy draw that happens right at the appliance's startup phase. Think about when your fridge's compressor first kicks on and makes that familiar humming sound. In that exact fraction of a second, it is gulping down way, way more electricity than its normal continuous rating. So the bulletproof solution to that surge problem? The 3x rule. To stop this sudden inrush of current from tripping your breaker or completely shutting down your solar inverter, always use a safety factor of 3 times your continuous watts when you're sizing your equipment's max capacity. So if your fridge pulls 400 watts continuously, your setup better be ready to handle a 1200-watt spike for a few seconds. Moving right along to step 2, daily energy consumption. Okay, now that we know the raw power draw, we need to calculate how much energy the fridge actually eats up over a full 24-hour period. And guys, this is where so many people make a critical math error. You absolutely cannot just multiply your continuous wattage by 24 hours. Why? Because fridges cycle on and off all day. That compressor isn't running 24/7. It only fires up when the internal temp gets too warm. So instead of just guessing, you really need to plug in a kilowatt meter to get an accurate, real-world reading over a full day. Let's look at some actual numbers from real-world tests. In these tests, the appliance doors were opened 5 times a day for about 20 seconds each, because, let's be real, you're going to open the fridge to grab a drink, right? Under those exact conditions, the small unit consumed 230 watt-hours daily, while the large unit chewed through 900 watt-hours. All right, step 3, inverter losses. This brings us to another huge trap for off-grid planners: the energy that just vanishes by keeping your AC inverter turned on. See, your solar panels produce DC power, and your batteries store DC power. But your kitchen fridge, it needs AC power. To bridge that gap, you use an inverter. But here's the kicker: an inverter drains your battery even when it's just sitting there idling. A small inverter loses about 250 watt-hours a day doing absolutely nothing. And a large one? It can waste 500 watt-hours or more every single day just staying awake. Which perfectly illustrates why you just can't ignore inverter drain. It's like a hidden tax on your battery. We have to combine our numbers to get the true picture. For the small setup, adding the 230 watt-hours for the fridge and the 250 for the inverter gives us 480 watt-hours per day. For the large setup, we add the 900 watt-hours for the fridge to a hefty 500 watt-hours for the inverter, bringing our total daily need to 1400 watt-hours. Next up, step 4, battery autonomy. Now that we have our highly accurate daily energy needs, we have to tackle a critical survival question: what happens when the sun refuses to shine? You aren't always going to have perfect, clear blue skies. You might get hit with a severe storm or a long stretch of heavy overcast weather. So, the golden rule in off-grid solar planning is to size your battery bank for exactly 3 days of autonomous running. That means your batteries alone should be able to run the fridge for 3 straight days with zero help from the sun. Applying this rule of 3 is super simple. We just multiply our daily needs by 3. Our small setup needs a 1,440 watt-hour battery capacity to safely ride out a multi-day storm. Meanwhile, that large, full-size setup, it demands a massive 4,200 watt-hours of battery storage to stay safe. So when you're shopping for batteries, these are the target capacities you're looking for. Okay, step 5, solar panel calculation. Finally, we need to figure out exactly how many solar panels it takes to reliably recharge that battery bank every single day. We know the size of the gas tank, now we need to size the fuel pump, right? But to do this, you can't just assume the sun is blasting at full strength from dawn till dusk. We need to find your local peak sun hours. This is the average daily hours of fully usable solar irradiance for your specific geographic location. You can easily pull this number from a free solar map over at the National Renewable Energy Lab's website. Let's ground this with a real example. Say you live in Illinois. According to the NREL data, Illinois averages about 4.2 peak sun hours per day. That means even if the sun is technically up in the sky for 12 hours, you're only getting the equivalent of 4.2 hours of maximum full-blast power generation. So, the math here is to divide our total daily energy needs by that 4.2-hour peak sun factor. Doing that, we see the small setup needs roughly 343 watts of solar panels to fully recharge the battery in one day. The large setup, obviously needing way more energy, requires around 1,000 watts of solar panel capacity sitting out there on your roof or in your yard. And that brings us to our final step, practical application. Let's take all this theoretical math and make it real. What does this actually look like when you buy the gear and wire it all together? Well, practically speaking, for the small system, you could wire 4 standard 100-watt panels together in a series parallel setup. That gives you a nice 400-watt input, providing a very comfortable buffer over the 343 watts you actually calculated. Now, for the large fridge, you could use 3 heavy-duty 395-watt panels wired in series. That generates just over 1,000 watts, making sure you can keep that full-size fridge humming along even if there's some light cloud cover. So, there you have it. You've seen the raw numbers, you've seen the hardware configurations, and most importantly, you now know how to dodge those hidden traps like surge power spikes and sneaky inverter losses. You possess the complete step-by-step roadmap to calculate your exact solar needs. So, take a look at your own kitchen. Think about the next time a massive storm knocks the grid out for 3 solid days. Will your current backup plan actually keep your food fresh, or is it time to start building your own energy independence today?